All right, let's take a look at the optimization procedure. Now, the middle parts are the parts that students usually have trouble with, but once you get the hang of it, it's actually kind of the easiest part. The harder part is the part that the computer can't do for you, the part that you have to do with your own head, which is getting the right setup and getting the right interpretation, right? So this stuff is all basically mechanical. Now, what this stuff is, let me show with a very generic example. Let's see, this marker is not super great. Let's go with this one. So let's say we've got a function f of x, right? So we don't have really much to interpret at all. Our setup is just going to be some function that we are given. So let's just go with a generic quadratic function. So we'll say a x squared plus bx plus c. So a, b, and c, these could be any sort of numbers, right? They're just placeholders for us. And you'll see with the problem set this week that, you can swap these out for specific things and you can solve some of the simpler questions from our problem set. The harder ones are going to be the ones where you have to set up and interpret stuff. So we've got this. Now, what do we do to solve for our first order conditions? Well, first order conditions, this is when we say, let's find f prime, our first derivative, set it equal to 0, and then solve for x. It's going to look kind of intimidating, but I promise it's really not that bad. So for this, we're looking for f prime. I'm going to be kind of lazy here and drop some, this parenthesis x. Here, just power function rule, the 2 comes down, 2 times a times x to the 1, plus b, the 1, there's implicitly a 1 up here. It's kind of implicitly an x to the 0 here also, right? X to the power of 0 is just 1. Assume a 0. We bring the 1 down, 1 times b is b, 1 minus 1 is 0, x to the power of 0 is 1, so we don't even have to write anything, and then this is just a constant, right, that goes to 0. So we've got our first derivative, and as long as we're here, let's set ourselves up for step 3 also, right? I just kind of, as a matter of habit, intermingle these two. As long as I'm doing a derivative, I just go a little bit further and take the next derivative, which is our second derivative, and we're going to ask about the sign. So the sign is going to be less than 0 for a max, or greater than 0, a positive second derivative for a minimum. And we'll explain that in a second. So f double prime, this is going to be 2 times a, x becomes just 1, b, that derivative becomes a 0, right? That's just a constant. So our second derivative is just 2a. So is that greater than or less than 0? Well, it depends on the value of a, right? So if a is 42, well, then we've got a positive value. We would be looking at a local minimum. All right, but let's come back to the first order condition. We want to set this equal to 0, and then we want to solve for x. All right, so I'm just going to take this whole mess, throw this over here. What do? We subtract this b, so we've got a minus b equals 2ax. 2ax. Divide both sides by 2a. And we've got x, I'm going to call this x star, right? This is our solution x, is equal to negative b over 2a. So this is where our first derivative is equal to 0. When x takes on this value, whatever that value is, we have found the point where we're zeroing out. So let's show a graph here to make some sense of this. So we've got x, we've got f of x, and what that looks like is, well, let's just assume a, b, and c are all positive, just to start with. So we know that x squared is just a parabola, right? It's just going to look like this. A times x squared is just going to stretch that out. So if we said 2ax squared, then instead of something kind of like this, we're going to stretch it out. It's going to be steeper if we made it say 1/10 x squared, it would be a really shallow parabola, right? So this is, well, the a is coming in here, but really the action in this case is with b, because with b, we're kind of distorting things also, right? So bx, well, that's just a line, right? That's like y equals mx plus b, except now we've got b is m and c is b. Don't worry about that. These are all arbitrary. They're just placeholders. We just gave it a slightly different label. All means the same thing. But this bx part, the bigger b is, the steeper that line is, right? Or if it's negative, we would have a downward sloping line that we're adding on top of that parabola, right? So let's say we've got a line like this. We've got a parabola from the ax squared, and then that parabola is going to kind of twist up on this side, and it's going to twist down on this side. So we're going to get something that's maybe a little shallower here and then steepens over here, right? But we still have all the information we need to get where does that flatten out. So I'm going to draw that in a second to drive home what this means. But really quickly, the C, this is just going to move the whole thing up or down, right? So we've got some parabola. Let's say B is 0, right? Let's ignore this. Let's say A is 1, so we just have our standard x squared parabola, plus C. Well, if C is, say, 10, then our parabola is just going to move up by 10, and it's going to hit this axis at a value of 10. But our generic shape for this is going to look something like this. Right? I would really highly recommend throwing different equations into Wolfram Alpha, because that's going to help you to see what it looks like without getting too bogged down in the details. You can let the computer do the hard work for you. Like I said, these are the things that the computer can do, right? They're mechanical. They're kind of annoying. There's room for error. But at the end of the day, you don't need to be smart to do these. You just follow some rules, which is why the computer can do them. The setup and the interpretation is the hard part. But before we get to there, let's just drive home what's going on with these parts. So we're saying f prime equal to 0. F prime is telling us the slope of this function at any given point. So if we look at the point where x is equal to, right, so in this case, let's say maybe it's just a tiny bit off of 0. But whatever it is, this is negative b over 2a, right? So when x takes this value, right, let's just say it's 1, 1, and 1, then this is going to be minus 1 over 2. This will be minus 1/2, right? It'll be just a little bit to the left of our y axis. But we're not going to be super precise, right? We're just really concerned with the high-level ideas here. So where this slope is equal to 0, that means we're looking at the slope at our critical point, our x star, is 0, and that means that we're going somewhere, right? This is the second order condition we're going to talk about in a second, but right now we can see our function is declining, right? Whatever f of x is, whatever interpretation we want, it's getting smaller, and then it hits 0, it flattens out, and then it gets bigger, right? This is what we mean by a minimum, right? It gets smaller, it stops getting smaller, it hits the smallest value it has, and then it gets bigger. Or if we had a parabola that opened downward, we would get bigger, 0 out, then get smaller. So here's the second order condition. Right, so this f prime is telling us about the slope of our function f, and then f double prime is telling us about the slope of the slope. So this point where we have a slope of 0, let's use a red marker to denote f prime. Hopefully it's distinct enough from orange for just f of x. But f prime of x, right here at our minimum, it's going to take a value of 0. And in this case, we can see we've got a negative slope, and then we go to a positive slope. So whatever's going on, f prime is something like this, where f is our original parabola. And then let's do this blue, our second derivative. this is just going to be a constant that's going to represent the slope of this line. Now in this case it's a line because we're looking at a parabola, but if we had, say, x to the squared, x to the 3, then our first derivative might be a parabola where our underlying function would be, say, a cubic. There's all kinds of functions we might draw, and again, play around with Wolfram alpha, but what we want out of this is something a little bit more general, right? We don't want to say, I'm going to look at a function, figure out what it is, and then solve it accordingly. We're just going to say, let's take a function, let's do some derivatives, and let's solve, and we don't even need to know what this looks like to get to the right answer, right? We're not in real life going to be dealing with these nicely behaved functions. In an econ undergrad program, yeah, we're dealing with nice, well-behaved functions, but if you're, say, trying to use this setup, right, this optimization procedure to, say, solve a machine learning problem, in a case like that, you might have a very complicated underlying function. So, our second derivative, 2a, in this case, maybe it's something like, what do we want to call this slope? Let's say this slope is like positive 3 or something like that. All right, so here's f double prime. The second order condition, we want to see what is the sign of this at our critical point. And what we can see is that f double prime at x star, well, it doesn't matter what the value of x is in this case, as long as a is positive, right? Let me make sure that this makes sense. A being positive, so if we put in a really big value for x squared, we'd have a positive times a big number. All right, that makes sense. Really big negative number, we're going to have negative 1,000,000 times negative 1,000,000 is going to be, is that a trillion or a quadrillion? It's going to be a very big number. Right? So as long as a is positive, this is our basic parabola shape. And you can see that this is basically driving the result in this particular example, right, for this nice, well-behaved polynomial. But since it is since it is positive, what it's telling us is that when we get to this critical point, we have a slope of 0 at that point, but that slope is getting bigger, right? Our f prime is telling us that we go from 0 slope to something bigger than 0, which means we must be going to a positive slope. So we start our critical point. As we start there and move to the right, we know that we're moving away from a smaller value towards a bigger value, and that's why when f double prime is less than 0, we're looking at a local minimum. All right, so that is the mechanical stuff. You're seeing this stuff in Khan Academy also, but here's sort of a quick and dirty version of this. I'm going to stop here, and I'm going to address a couple other points in the next video.